Okay, guys, so this is going to be a review or an overview of projectile motion and how we calculate it and what it's all about. Um, to talk about projectile motion, it's just basically any body that's in the air, um, path or motion, whether it's a ball, whether it's a human body. And again, it's dealing with nothing that has a motor. So anything that has a motor or propulsion is not a projectile motion. And there's basically because there's two external forces that we say are acting on these, creating the path of travel. That's gravity, and remember, gravity only acts in the vertical, and then also air resistance. There's many forms of which air resistance can play on the body. It could be a slowing down, a speeding up, a pushing up and raising. But for our situation here, we are going to act like air resistance is negligible because of the motion we're talking about and the items we're talking about. So we're going to act like we're in a wind tunnel. Okay, so we're going to take air resistance out of our equations, and it produces a parabolic motion. So it's a parabola. It looks like this. So it's going up and down. And as we look at this, I want you to focus the bottom one because what we're going to end up doing a lot is we break this into two components. And here, I'm sorry, can't draw a straight line. This is the apex, and so this dotted line allows us to break this up into the up and down segments. So you're going to have two segments, up and down, of your parabola. And if we leave from the same area of the ground and land on the same area of the ground, then we have an equal parabola, and T up equals T down. But you'll see here you have vertical displacement and horizontal displacement. We're going to talk about how to break up your initial velocity vector into the vertical and horizontal components. But there's many forms of this motion: shooting a basketball, throwing a football. And what you'll notice here is that these don't follow that. If I take this down, these don't follow along the line where the point of release matches the point of hitting the ground. Point of release doesn't match where it goes through the basket. But these are all the parabolic paths that we follow in going through the motion, as well as somebody who's jumping over a bar in a high jump. And again, you leave the ground lower than you land the ground. So these are all possibilities in human activities. And then you have what we see a lot of these parabolic motions, and when they use these equations is home run derbies and ball tracks. They look at the projection angle and the velocity of the baseball at the initial. They calculate the estimated distance upon which it lands. And this is how something that goes in the third upper deck, they say has a longer trajectory because they just calculate it as if it was hitting the ground. So that's where that all comes from. And then you can also do what's your velocity at which you hit the water is if you jump off the cliff and you jump up and jump down, you can find all that motion out for yourself, whether you jump in the horizontal or vertical. And again, that's a motion. This one down here is looking at the center of mass, and that's going to be your projection. So going forward, there's going to be three basic factors that we're going to look at that are going to have an effect on what you do and how you perform as a projectile, whether it's a ball, whether it's you as an individual jumping. And that's what your original projection velocity is. And that is going to be your initial velocity. So it's velocity initial. Okay, and we're going to talk about how to break that down into different components in a little bit. But then you also have the projection angle, and that's the angle at which you take off from the right horizontal. And typically we do it from the right horizontal, but if you went to the left, we could do it from the left horizontal as well. But this allows you, with the velocity and the angle of projection, that allows you to use cosine and sine to break the components up into vertical and horizontal velocity. And then you also have the projection height. And this is what they look like here. So if you look at this picture, here is the initial velocity vector. This is the theta. And then down here, you have the projection height. So the height from the ball to the ground is projection height. Now, if there is a basketball hoop right here, then we could do the height would be this right here, because you're going to see how it lands through the basketball hoop. So that's where all this comes into play. So remember, these are the three factors that affect projection path: velocity of projection, angle of projection, height of projection. Okay, so here we have one of the very important parts of this, and this is projectile motion equations. You're going to have multiple equations, and what you need to understand is the concentrated accelerated motion equations only deal with the vertical motion. And the vertical motion, so the A in all of these is negative 9.81 meters per second squared, which is the motion due to gravity. Okay, so when we say constantly accelerated, the acceleration is the constant because it's a constant rate of change due to gravity. These equations look like this, where this is the vertical velocity, so VF is final, VI is initial. Okay, you know what A is. So T is lowercase in this case because we separate it into halves. So there's a T up and a T down, and those are the two halves of the parabola. So the time it takes to get to the top of the parabola and the time it takes to get to the bottom of the parabola. D is interesting because D can be seen as S or it can be seen as H. And essentially it's the height of wherever the projection begins to the apex, or it's the apex down to wherever it lands. So it's this distance on the parabola. And again, this is the T up part of the parabola, T down part of the parabola. Okay, so the important part is these equations only deal with the vertical component of projectile motion. And we'll talk more about VI and VF and how to calculate those in a second. But if you're dealing with horizontal motion, then you're talking about the range at which something goes. So the range is how far something travels in the horizontal. And then so you see a big T here, and that is time up plus time down. Okay. Now for those equations and those situations where you start and you stop at the same height, then it's basically 2t. But now you have the h, and that's the horizontal component. So when we look at it, that is going to be the components that we decompose in the horizontal. And we'll show you how to do that here shortly. So remember that the equations of constantly accelerated motion are the three that you use in the vertical. And then the range is only horizontal. So in the range, there is no effect of gravity. Gravity only behaves in these three equations. Okay? So how does this look in a problem or in the real world? Well, I would start like this. I would give you a problem saying, okay, something left at 10 meters per second with an angle of projection of 35 degrees to the right horizontal or the ground. In this case, we're going to say we kicked a soccer ball. Okay, and we just assume that it goes up and down. There's no curve to the soccer ball. It's not bending it like Beckham. It's just a normal kick. Well, this is what this would look like. Okay, so if I have the known, which is 10 and 35, now I want to break it up into the vertical and horizontal components. And that looks like this. So if I do my right triangle, I know that this is my VH, this is my VV, this we'd call our hypotenuse, right, or our original. And so I break it up. So VV equals hypotenuse times sine of theta. VH equals hypotenuse times cosine of theta, right? So cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. So you have these equations, okay? And so you essentially just plug it in. Sorry, that should be 35, and this is 10 cosine 35. So breaking it down, we have in the vertical, it comes out to be 8.19 meters per second, and in the horizontal, it's 5.73 meters per second. So now you have what we consider your new velocities. This is your velocity in the vertical. This is your velocity in the horizontal. So what I want you to do after you do that, and I do this on all mine, is if you don't do this, you're going to hurt yourself, is get rid of the 10 because you're going to use this in the equation. It's not going to be good for you. Okay. So the other thing I end up doing is I will create a little note for myself, VI, VF, A, D, T, and I'll have this as my T up, and then I have my T down, and I have again VI, VF, A, D, T, and then I will also have my range, and so I'll have R, big T, and V in the horizontal. So I take this part right here and I write it out every single time I do a projectile motion, because what you're going to do is you're going to fill in the knowns, the known quantities. And so I'll show you what that looks like here shortly. Okay, so now what I've taken this little unit here and I put it up in the top portion of it. And so now I'm going to go ahead and fill in what I do know. And so we can begin to fill out what we don't know. Now we've already identified what VH is, and that was 8.19 meters per second. We've already figured out, we know what A is for all these, because these are all the verticals, so it's 9.81, negative 9.81 meters per second squared, meters per second squared. Okay, now I know what the initial velocity is, because we calculated that, and that's going to be 5.73 meters per second. And what I do know is I know what my final velocity is going up. Remember, so this is my parabola going up, this first part. Okay, so we look here, and this is my D, and this is VF up here, this is VI, and so at VF at the top of the parabola, my velocity is 0 meters per second. And so now what I'm going to do is I'm going to use my equations of uniformly accelerated motion, or constantly accelerated motion, to determine what D and T are. And so there's a number of equations I can use. And I'm not going to write them all out here. You can go back and look at them. But the first one I'm going to use is VF equals VI plus AT. And if you fill in what you know, you can solve for what you don't know. So in order to do this, so I know VF is 0, I know VI is 5.73 plus negative 9.81 T. And this ends up being, if you just rearrange everything, T equals 0.58 seconds. Sorry, that's an 8. Okay, so at this point, I can come back up top and I put that into my T, 0.58 seconds. So now I need to know is my D. And the interesting part with this is there's a couple ways I can go about it. Now that I figured out T, I can use the D equals VIT plus 5 AT, or I can go this one, which I would just use, and that's going to be VF squared equals VI squared plus 2AD. And I just plug everything in and solve for D, and D ends up being 1.6. I think I wrote down 2. It might be 7, but meters. Okay, and so now I've put that over 1.62 meters, and that's, so now I solve for T up. If I said it was, if I went for, like we said, soccer ball going from ground to ground, then what I do know is that this part of the parabola is a mirror image of this part of the parabola. So I know that VI, because I'm at now, this is my VI, this is my VF. So I know my VI is 0 meters per second. My VF is the same velocity as a start, but in the negative direction, because I'm going back to the origin. The D is the same, and the time is the same. Seconds, sorry. So what T is for the range, now I can go to the range and figure out the horizontal. In this case, T is simply 2 delta T, 2 small t's, because T in the range equation equals T up plus T down. In this situation, T up equals T down, so delta T, or big T, just equals 2 t up. So it's simply going to be 1.16 seconds. And so the range equation, if I look at the range equation from before, range equals horizontal velocity times t. I know both of these, so I can just calculate that out and figure out how far I traveled in this path. And this is the range down here from this port to this point. That's our range. Okay, so then you can calculate the range. We'll talk about all this in class, and so how you determine differences with you take off higher or lower in that whole process. So when all said and done, what I want you to do is you need to figure out what vertical velocity, what horizontal velocity, how those are comprised with when I give you an initial velocity. How do you decompose that using cosine and sine? And then you look at the equations of uniformly accelerated motion, and you figure out what you do know, what you don't know, and you use the equations to solve for the unknowns. Sometimes what I can give you is if I give you the range of something and I tell you how far or how long it took to get there, what can you calculate from there? Well, then you can calculate the horizontal velocity. Okay, so you need to know what's unknown and what to solve for, and you'll be able to do this. So we'll have some fun in class.